Welcome to the 16th lecture in our course on quantum mechanics. In the previous lecture, we began our look at quantum entanglement. We saw that a composite quantum system, a system made up of two or more particles, can be in an entangled state. In an entangled state, the pieces of the system do not have definite quantum states of their own. Only the whole system has a quantum state. Now, the properties of entangled systems led Einstein, Podolsky, and Rosen, EPR, to argue that quantum mechanics could not be a complete description of nature. EPR said there must be things that are real, but are not part of the quantum description. In the example that we studied, we could either predict X or Z of one spin just by looking at the components of the other spin. And according to EPR, this meant that both X and Z values must already be real for the spin we're predicting. Now, Bohr responded to the EPR argument. We described his counter-argument as complementarity at a distance. And based on his critique, we concluded that the EPR argument was not airtight. So the matter stood for almost 30 years. Then, in 1964, John Stuart Bell, an Irish particle physicist, reconsidered the EPR argument and thereby changed the world. Bell showed that the EPR argument is not merely weak, it is exactly wrong. He showed that the physics of quantum entanglement actually leads us to a very different conclusion about the nature of reality. Bell's result is so astonishing, its implications so far-reaching for our view of the world, that we will spend this entire lecture following his reasoning for ourselves. So pay close attention. Something truly amazing is in the works. Let's begin. How does Bell proceed? First, he boils down the EPR argument to its essentials. He identifies three propositions about the world. Each proposition may be true or not, but here are three propositions about the world. And the first one is entanglement. That proposition states that quantum mechanics correctly describes the behavior of entangled systems. In particular, correctly describes the behavior of a pair of spins in a total spin zero state, like we analyzed last time. And notice that this proposition is something we can check. We can check it by doing experiments on pairs of spins. And when we do those experiments, the predictions of quantum mechanics are confirmed. So that's the proposition of entanglement. The second proposition is the proposition of hidden variables. This says that the results of our measurements are actually predetermined, that we use probabilities to describe them only because we lack detailed information about the hidden variables that determine the results. If we only knew those hidden variables, we would be able to tell what the results would be for sure. And this is Einstein's view of the probabilities in quantum mechanics. Then there's the third proposition, the proposition of locality. This states that the behavior of any particle is locally determined. That is, it's governed by the particle's own variables and the immediate circumstances, including any measuring apparatuses and so on. What happens here is determined by things which are here. There's no magical influence from far away. Note that if I am getting my instructions by radio, my actions are still locally determined because my radio receiver picks up local radio waves, the radio waves in my vicinity, which of course may have originated somewhere else and traveled here. So even if I'm getting my instructions by radio, my behavior is locally determined. Bell says that the EPR criterion of reality is really based on this idea of locality. Remember, we had two particles, number one and number two, which were far apart. And we made measurements and so forth on number one. And locality says that these actions that I perform on number one cannot have any immediate effect on number 2 because they happen far away. I mean, remember Einstein's theory of relativity. One of the consequences of that theory is that nothing can travel faster than light. So it will take some time for any physical influence, like the radio instructions in my example, any physical influence to reach all the way from number 1, where we're doing the manipulation, to number 2. So according to the EPR criterion of reality, what we do on particle number 1 does not count as a disturbance of particle number 2. And that's why, according to EPR, what we find out about from particle number 1 that allows us to predict particle number 2 must reflect something that is already real about particle number 2. That was the EPR argument. So there are 3 propositions. There's entanglement, hidden variables, and locality. And only the first one, entanglement, is directly checkable by experiment, but the other 2 represent common sense assumptions about the world. They certainly represent the view of the world advocated by EPR. So here's the EPR argument according to Bell. Entanglement, the behavior of entangled quantum particles, together with locality, which encompasses the EPR criterion of reality, means we have to accept hidden variables. Entanglement plus locality means hidden variables. We have to accept that things are really predetermined. So, given the behavior of 2 spins in a total spin 0 state, and assuming that the particle behavior is locally determined, then, according to EPR, the results of quantum measurements must be real before we measure them. There must be hidden variables that are not included in quantum mechanics. That's the EPR argument. Now Bell does something very clever indeed. He does not start out with quantum mechanics. Instead, he imagines a world of his own, a world in which there really are hidden variables that function in a local way. And this is easy to do. It's easy to imagine a world like this because this is the world of our common sense. Bell thinks carefully about what that world would have to be like. And he proves that this imagined world cannot be the quantum world. It cannot be the world as it really is. Okay, so let's take a look at the common sense picture of the world. This is the cartoon version. We have particles flying all over the place, obeying the laws of physics. So the question is, how do the particles know what to do? Well, we imagine each particle carries along with it a book of instructions. The instructions say things like, if you fly through an electric field, do this. If your spin is measured, do that, and so on. This book of instructions, of course, is just a metaphor for the real physical properties of the particle that will determine its behavior. And the instructions might or might not be deterministic. They might say, do this or do that with such and such probabilities. And so if we like, we can equip our particles also with dice. And whenever they need to generate some randomness, they just throw the dice and figure out what to do. The key point is that each particle throws its own dice. The behavior of a particle here is not determined by the throw of the dice of a particle over there. And so in the general kind of experiment we're going to consider, we have 2 particles that interact with each other and they fly off in opposite directions, and then we observe that the behavior of the particles is correlated in some way. So the common sense view is that the particles are cooperating based on a previous agreement that they struck, so to speak. That the correlations of the particles are all explained because they've coordinated the instructions that they're carrying. They agreed on things like, you have spin up and I'll have spin down. And these agreements are written down in their instruction books, and once the common instructions are agreed to, the particles carry them away, and then they act independently on the instructions they have. That's the common sense view of how correlations between particles can arise. And so Bell's imagined world, the world of our common sense, obeys two assumptions: hidden variables and locality. All of the correlations between particles are explained by hidden factors, namely the secret instructions carried by each particle, the secret instructions which may have been devised in agreement with other particles. And if there's any randomness, it is purely local randomness. Each particle has its own dice. And so, based on these assumptions about his imagined world, Bell derives a relation, a mathematical inequality that must hold true in any world governed by these local hidden variables. This inequality is called Bell's inequality. And there are many different versions of this inequality, and we'll take an especially simple one. Now, Bell's imagined world actually looks a lot like quantum mechanics. There are spin 1/2 particles, and if you measure any spin component of a spin 1/2 particle, you only get the values plus 1/2 or minus 1/2, just like in quantum mechanics. And each particle has more than one spin component that might be measured. That's something like complementarity. We can measure spin in the x direction. We can measure spin in the z direction. We can measure some other component of the spin in between. So we suppose that we have a pair of spin 1/2 particles. Call them number 1 and number 2. And on spin number 1, we can measure either spin component A or we can measure spin component B. And on particle number 2, we can either measure spin component C or spin component D. And later we'll choose what directions these are. For now, they could be anything. So there's A and B on particle 1, C or D on particle 2. So that means there are 4 possible combinations of measurements. We could measure A and C together. We could measure A and D together. We could measure B and C together, or we could measure B and D together. So in each of those combinations of measurements, we have a particular question that we're going to ask. How likely is it for the measurement results of the two particles to actually agree? How likely is it that the measurement results are both plus 1/2 or both minus 1/2? And we could write that something like this: the probability that A equals C is the probability that A and C measurements yield the same result. The probability that B equals D is the same thing for B and D measurements, and so on. There's one such probability for each combination of measurements. The probability that that combination of measurements yields agreeing results. Now remember, we are in Bell's imagined world. In this world, there are hidden variables and locality holds, which means, hidden variables means that the values of A, B, C, and D are all definite. They all have definite values. In any given experiment, we only find out 2 of them, but in every particular run of the experiment, all 4 of them actually have a value. And locality means that the choice of which measurement we make on particle 1 does not affect the result that we get for particle 2, and vice versa. These are the 2 assumptions. Now, in our imaginary world, let's suppose we find the following experimental data. Let's suppose we find that the probability that A and C agree is 0.85. That is to say, A and C agree about 85% of the time. And let's also suppose that B and C agree all the time. The probability that B equals C is 1. They always agree. And also let's suppose that the probability that a measurement of B agrees with a measurement of D is also that's also 0.85, that B and D measurements agree 85% of the time. We're just going to assume that these are observed facts about the system. What can we say then about the probability that a measurement of A agrees with a measurement of D? Well, let's think about it intuitively for a minute. We know that A and C agree a lot, 85% of the time. And we know that C always agrees with B. And we know that B agrees a lot, 85% of the time, with D. And so A and D will have to agree pretty often. Let's take that intuitive argument and make it mathematical. Let's make a diagram, a chain, A and C and B and D in that order. And all of these have definite values because of hidden variables. So how likely is it that A agrees with D? Or to turn it around, how likely is it that A disagrees with D? For A to disagree with D, then somewhere along this line, there has to be a disagreement somewhere. Now, the disagreement can't happen in the middle, B being next to C, because B and C always agree with each other. And A disagrees with C only 15% of the time. B disagrees with D only 15% of the time. So you conclude that A and D disagree no more than 30% of the time, and maybe less. They disagree no more than 30% of the time. So they agree at least 70% of the time. The moral of the story, the probability of agreement between A and D is at least 0.7. It might be more. A and D could be in more agreement, but it can't be less. And this is a particular example of Bell's inequality. Given our assumptions about the imaginary world, this inequality must hold, that is to say, it must hold in any world governed by local hidden variables, particles that operate according to separate instruction books. And that's pretty cool. We've made a definite prediction. And we can ask, is it true? All right, let's leave Bell's imagined world behind and go back to the world of quantum mechanics. And we're going to set up an experiment that looks just exactly like the one in Bell's imagined world, and then we'll see whether the results of the laws of quantum mechanics lead to the same conclusion that the other assumptions led to in Bell's world. So here's the experiment, the Bell experiment. We start out with 2 spins in a total spin 0 state. And to figure out what happens, we're gonna do a little background analysis here to get it figured out. Let's just imagine we measure spin components along 2 axes, A and C. A for particle 1, C for particle 2. And what's the probability that the results will be equal in quantum mechanics? Well, that depends on the angle alpha between the 2 spin axes, the A and C axes. And so think about it. If we have a total spin 0 state and we measure A on number 1, then whatever result we get, we know that the state of number 2 is exactly the opposite. So we can use our previous analysis, our analysis from lecture 10 about spin, to figure out, if we know the state of particle number 2, we can figure out the probabilities for a measurement of some spin component of it. And it needs a little thought. But we actually have everything we need to do this in lectures 10 and 15. So we can review the material there if we have any difficulty. But it's actually not too hard. If we let alpha be the angle between the A and C measurements, we can actually just make a chart of probabilities. In the first column, we have various angles between the 2 spin axes. And in the other column, we have the probability that the 2 measurements will agree in outcome, will either be both plus 1/2 or both minus 1/2. So if the angle between the 2 is 0 degrees, the probability of agreement is 0. If the angle is 45 degrees, the probability is 0.15. They only agree 15% of the time. If the angle is 90 degrees, it's 0.5. If the angle is 135, it's 0.85. And if the angle is 180 degrees, the probability that the 2 measurements agree is 1. Now, some of those entries are really easy to understand. If the angle between the 2 axes is 0, that means that A and C are really the same spin component. A and C are really the same axis. And for a total spin 0 state, the results of measuring the same spin component on both particles will always disagree. A will never be the same as C, and so this probability is 0. And in the same way, if the axes A and C are opposite to each other, then because it's a total spin 0 state, the spins must be opposite, and therefore the probability that A and C agree is actually 100%, 1.00. So we have a chart of probabilities that will let us calculate the likelihood that two spin components agree with each other if we measure them on a total spin 0 state. Now let's describe the experiment. We're going to have two particles in a total spin 0 state. We're going to measure either A or B on spin 1, just like we did in the imaginary world. We're going to measure C or D on spin 2, just like in our imagined experiment in Bell's imaginary world. And now we're going to choose exactly the axes that we're going to use. And I'll describe it in this way. A, spin component A, points north, let us say. And spin component B points northwest. And over on particle number 2, spin component C points southeast, and spin component D points east. So we have a set of 4 directions, 2 of them for particle number 1, 2 of them for particle number 2. We'll choose these directions for our experiments. And now we can calculate the probabilities that the measurement results will agree with each other. For the combination A and C, spin component A and spin component C, the angle between those two directions is 135 degrees. That's 90 degrees plus 45 degrees. And so, consulting our chart, the probability that A and C agree with each other is 0.85. They agree with each other 85% of the time. Spin components B and C are along directions that are exactly opposite to each other at 180 degrees angle from each other. And so the probability that the results agree for a total spin 0 state is 100% of the time. They always must agree because they're in opposite directions. And for the combination B and D, these are at an angle of 135 degrees from each other, and so the probability that their results agree is 0.85. Again, this is just like the imagined experiment. Remember what we're doing? We're finding out what the predictions of quantum mechanics are for an experiment done on a pair of particles in a total spin 0 state. Now, if we were in that world that was governed by local hidden variables, the imagined world of John Bell, then Bell's inequality would have to apply. All of these results that I've said so far are just like that experiment, so what follows must follow. That the probability that A agrees with D has to be at least 0.7. So, what does quantum mechanics tell us? What does the quantum mechanics of a total spin 0 state say? Well, the A-axis and the D-axis are 90 degrees apart. So the probability that the results of measurements on the A and D axis agree with each other is 0.5. And this violates Bell's inequality. We've come such a long way that it's easy to miss how stunning this conclusion is. We need trumpets to play and fireworks to explode. Here's what we did, following Bell's own argument. We imagined a world governed by local hidden variables. That is to say, the hidden variable proposition and the locality proposition hold good in this imagined world. And based on that set of assumptions, we derived a conclusion about the probabilities for joint measurements of two spins. And that conclusion was called Bell's inequality. And then we compared all this to a real quantum mechanics experiment done on the entangled state, total spin 0. And we found that Bell's inequality was violated, was not true. Therefore, the imagined world of John Bell cannot be our world. Remember, the EPR argument is that entanglement, together with locality, implies hidden variables. Bell tells us that this is 100% wrong. Because entanglement, locality, and hidden variables are actually inconsistent with each other. If you pick any two of them, the third one must be false. And by the way, we can test one of them. We can test the entanglement proposition. We can do lots of experiments to see whether quantum mechanical entangled particles have the predicted behavior. And we do that, and we find that quantum mechanics is confirmed, even when the particles are very far apart, kilometers apart. Bell's inequality has been decisively violated again and again. And so the entanglement proposition is very secure. We can rely on it. Therefore, we must either give up determinism, give up the idea of hidden variables, or we must suppose that entangled particles can somehow influence each other instantaneously over great distances. We must give up locality, or we must give up both. Now, Niels Bohr might have said that the hidden variables assumption is flawed at the outset because of complementarity. John Bell himself preferred to say that quantum mechanics is non-local, that widely separated particles do exert some kind of influence on each other. And either response is reasonable. But notice that either is an earth-shaking conclusion. One physicist, a Nobel Prize winner no less, has called John Bell's discovery, which is known as Bell's theorem, the most important discovery in the history of physics. This is probably an exaggeration, but it is a pardonable exaggeration. No discovery brings with it more startling philosophical implications. Think about our common sense view. Our view that what happens here depends only on the physical circumstances here. That particles effectively carry instructions, and if dice must be thrown to make randomness, the dice are thrown locally. That correlations between particles are due to shared instructions. This common sense view of the world is wrong. A final remark. Einstein died in 1955. Bohr died in 1962. So neither of them had a chance to hear about Bell's astounding discovery. Neither of them got to see the surprise twist at the end of the debate about EPR. And it's interesting to speculate about what their reaction might have been. Whatever else, though, I believe that both of them would have been flabbergasted by Bell's theorem. We're going to learn more about quantum entanglement later, especially in lecture 21. But meanwhile, we're going to continue on to some other stops on our tour of the quantum world. Our next stop is a weird and novel way of looking at quantum mechanics developed in the 1940s by Richard Feynman. The Feynman approach will help us understand more about electrons and photons, and this approach forms the basis of the most precise physics theory ever invented, the theory of QED, quantum electrodynamics. QED is the basis and the model for elementary particle theories right through to the present day. So next time, QED. I'll see you then.